is a two-dimensional union of rectangles. What about for the second example, B indexed by J? Okay. So it is a line segment now because it's only one-dimensional. And it goes from 1 to m minus 1, but also includes the first reference on the right-hand side, j minus 1. So it actually goes from 0 to m minus 1. Right? And the data space for the third example is, again, a line segment going from 0, this time up to n minus 1. Okay? All right, so the other thing that we want to be careful about is the notion of reference, and then we'll come to dependencies. Okay? A reference, and you guys are doing compiler, so this is easy for you. It is it's a syntactic property of the code. It is the occurrence of an array variable on either the left-hand side or the right-hand side. It's a read reference or a write statement. Okay, of a statement in the loop body. So in our examples, we have in each one there are 3 references. One is a reference to the left-hand side variable with a certain access function. Okay, it's a mapping from the iteration space to the data space. Every reference has that. It is associated with a function that maps the iteration space to the data space. Because a reference occurs within a set of loops inside some control structure of the program, and that corresponds to some instance of that statement, and that instance is associated with a point in the iteration space. But the memory location that is being accessed is some expression involving those indices, and those expressions lead you to some memory address, which is a multidimensional vector in the data space. Okay, so every reference is associated with a mapping from basically indices to indices, indices of the iteration space to indices of the data space. Okay, and in our example, these mappings are particularly simple, but in general, they can be arbitrarily complicated as long as they are affine or linear. Okay. All right, and then the dependencies is what you want to really figure out, which is which iteration depends on which others. Okay, if the loop body has multiple statements, then you want to say which iteration of which statement depends on which iteration of which statement. But in our examples, every time we are looking at a loop, there is only a single statement in the loop body, and that is enough of a simplification for us to understand all the principles. Okay, are you all with me so far? I'm really cognizant that this is a long day, so if you want me to speed up, I will. But if if this is fine, then I'll keep going. All right. So finding dependencies in general, it is an undecidable problem. If you give an arbitrary program and you are asked, which statement produce the value that's being read, you are in deep trouble. Okay, but we in the polyhedral model, we have a relatively simple example. What we've chosen is that we are going to look at programs which are loop programs, where the loop bounds are given by linear inequalities in the indices, and the memory access functions are all linear or affine function of the loop indices and parameters and size parameters. Okay, so m and n are size parameters. So what I just said is actually a big mouthful. So I just want you to think about, how many of you know the difference between linear and affine? Do you want me to tell you what the difference is, or should I go on? See, this is where it has to be interactive.
Yes, sir. Can you please just spell out the difference?
Okay. A linear function is like ai plus bj plus ck, where a, b, c are constants. I, j, and k are the indices. Those are the unknowns. So this is a linear function of the indices. An affine function is ai plus bj plus ck plus d, a constant. A linear inequality is something that is passing through the origin. AI plus bj plus ck equals 0. A linear equality. An affine equality is something that is shifted by a constant. So it allows basically the idea of translation. In addition to some linear function, you can also do translation by a constant. That's the only difference between linear and affine. Okay. And if some of you have taken a course in computer graphics or will take a course in computer graphics and we're thinking of linear transformations from from the perspective of light sources and all that, this is a very well-known technique that if you are in a 3D space, you can extend that and make it a 4D space with a special interpretation of that additional index. And whatever is affine can be thought of as linear with one extra dimension. So linear and affine are terms that we will be using interchangeably in the polyhedral model. Okay? And when you see someone talking about affine or linear, etc., just be aware that under the hood, it's all the same thing. There is machinery, and if you will have some practice with tools like ISL, you will see that the tools are way more sophisticated than the simple examples that I'm giving you. Okay. All right. So what is the problem that we want to solve when we want to do dependence analysis? You have many, you want to do dependence analysis of, that is element-wise and instance-wise. Okay. So you have a particular instance of a statement. That means a statement, let's say, in our example, we have only one statement, so there is no issue. In a program with multiple instances, you can think of a constant number of statement labels. And you take that statement label, and each one is associated with an integer point in a polyhedron. Because there are multiple instances, one associated with every point in the iteration space. Right? And what you want to do is, when you look at a statement body or a statement in isolation, it is simply a syntactic entity, like A of ij equals blah, blah, blah. Okay? So when a statement instance is being executed, then the question you want to answer is, which instance of which statement wrote the value that is being read by the reference? So let me go back to our examples. Okay. Yes, they're simple. Okay. My question to you is, if I am looking at the first example and I'm looking at the first read reference in this program, that is basically A of ij minus 1. Okay. And for this example, the answer is going to be very simple. You do a little bit of thinking and you can tell me the answer right away. Okay. Which instance of which statement? Well, which statement is, of course, the only statement in the program. That answer is easy, right? Which instance of this statement wrote the value that is being read by the reference aij minus 1 in the ijth iteration of the loop? Which iteration wrote that value?
ij minus 1.
Ij minus 1, right? Are you sure?
Yeah.
What if j equals 1? So the answer to that is subtle. For points sufficiently far from the boundary, it is ij minus 1, as you rightly say. At certain other points, it may be different. So the answer to my question, which iteration wrote the value that is being read by the reference aij minus 1 at iteration ij, is, if j greater than 1, then ij minus 1. Otherwise, what?
I might be wrong, but is it I minus 1 j plus 1?
In this case, no, because if you visualize the picture that I was drawing, I won't change the screen so rapidly because it takes time. I want to, the context switch is a little difficult. But imagine this point ij minus 1, ij, okay? And imagine that it is at j equals 1. It is reading memory location I0, okay? I'm assuming that the memory location is valid. There are no out of bounds references. So that memory location is being read. And the question that I'm asking is, which iteration wrote there in this program?
No iteration wrote it.
No iteration wrote there, right? Therefore, it means that the reader, the producer of this value, is none of the iterations, none of the points in the iteration space. Indeed, it is some point that came before the program started executing. Okay? It's basically an input dependence. All right? So, there are all these subtle things to be resolved when you actually do the dependence analysis and when you implement a tool that does dependence analysis. Okay? But the other thing that was very implicit and very obvious in your answer, which you may not be aware of, is that you want to find this set as a function of ij. When you said ij minus 1 is the iteration, that means at iteration I equals 5, j equals 7, the iteration that produced the value is I equals 5, j equals 6, etc., etc. But this is again a function. It is a mapping between iterations. Do you understand that? And do you see that clearly? In general, and if the example were more complicated, what the answer that you would get is some sort of a function of ij. In fact, even now, with this simple example, it is a function, it is a piecewise function. If j equals 0, it is a certain value, it has a certain value. If j is strictly greater than 0, it has a different value. Okay?
So basically, like, these boundary conditions make finding these dependency hard. Otherwise, we would just have a function of ij.
Yes, but the function is not necessarily obvious from the syntactic text of the code, and we'll go into that. We will see that analysis in good detail. Okay, because a iteration point reads a memory location. Our first example was deliberately simple because it was an iteration space of 2D and also a data space of 2D. An iteration point reads a memory location. Many iterations may have written to that location. You agree? So what you want to do is find the set of iterations that write into the memory location being read. Okay? And again, as always, it has to be expressed as a function of ij, the iteration point. Out of all these writers, find the most recent writer that is executed before the iteration ij. And then you have identified which instance of which statement produced the value that is being read. Okay? So let's work it out. We have to know the execution order, and I will draw in my figures the I-axis vertically downwards and J-axis horizontally to the right, so that my origin is at top left. Okay, because that notation, that choice of axes corresponds to arrays like Aij or matrices that that occur very frequently in the data space. Okay. So what is the execution order? I is the outer loop, J is the inner loop. So you have something like this. After you execute the first row, then you execute the next row, and then you go on and so forth, right? That is the execution order, and it happens to be exactly the lexicographic order between iteration points I1, J1 and I2, J2. Okay? I've thrown a new term at you, lexicographic order. You have a sort of very good intuition of it because you've all used a dictionary in your life, right? It is exactly that order amongst vectors of integers. 315 is lexicographically before 317. It's also lexicographically before 4 anything, right? So that is the order between points in the iteration space that we will be following, because we need to figure out this, because in order to figure out dependencies, you need to know that which of the iterations occurred before. Okay, and we are going to use the lexicographic order. Okay, so in example 1 and 2, this, they actually have the same solution, and we'll see how. Okay, even though the data space is different. Iteration ij depends on iteration ij minus 1 and I minus 1j, the neighbors on the west and north, provided you are sufficiently far from the boundary. Okay? So let us work out equation 2 now, example 2. So can you see this?
Yes.
Can you remind me, because I'm not seeing the PowerPoint in front of me, what is the statement body in the second example? Bj equals bar of bj minus 1 bj. Is that right?
Yes, sir.
Okay, so I'm going to draw my iteration space again. Okay, and I'm going to focus myself on this point ij. Okay, when I am executing iteration point ij, okay, I'm writing into this memory location, and I'm reading from 2 other memory locations, right? The analysis that I have to do starts from that. Okay, at this iteration point, I am reading memory location bj minus 1. Okay, and I'm going to draw that data space indexed by j like this over here. Okay, so this iteration point is reading this memory location, not the one vertically in this, but its neighbor. Okay, so you see that this is a mapping from iteration space to data space. Okay, now I am going to now study the inverse mapping, because the question I'm asking now is, which set of iterations wrote into that memory location? Which are the iterations that write into this memory location?
I comma j minus 1 for all I.
For all I, right? So this entire column of points in the iteration space are the writers to this. Okay? All right. Out of those, which are the ones that were executed before the current iteration point? And keep in mind, all of these questions that I'm posing are posed in the form of, my answer must be some function of ij. Okay? So out of all of these writers into this memory location, which occur before this point?
So all iterations such that your I is less than the current I, or your I is the same and your J is.
So you are talking about the set of all iterations I prime such that I prime is less than or equal to the I that I'm talking about, right? So it is all these iterations over here, right? Including the one on the same row. Okay? And now the question is, out of all of these, which in the execution order is the most recent? Out of
Just
all
the
of these
previous one, like
that
having the
is
same
the
eye.
most recent, right? So the analysis has gone through all of these steps to figure out something that you as a human would say right away. Oh, the most recent producer of this value is just the point on the left, sufficiently far from the boundaries, right? Now, if I ask you the same question about this other reference, BJ is updated using it's reading the value BJ. Who was the most recent writer in that memory location? The point on the north, right? Because we do the same analysis. Who are the candidates that write into that same memory? Which is the memory location being read? This one. Who are those writers? The iterations that write into that. Which of them happened before? And now this one, this one cannot happen before this one. Sorry, this one cannot happen before itself. So now the constraint is that I is strictly less than, I prime is strictly less than I. Okay, the execution order allows you to make that distinction. Okay, and out of all these writers, which is the most recent? This one. Okay, and therefore what I said on my slide is that sufficiently far from the boundaries, the dependencies in this example are identical to the dependencies in the first example. Every point depends on the value that is produced from the north and west neighbors in the iteration space. Okay? How are we doing for time? We're 45 minutes. Would you like to take a break? It's up to you. Like I say, it's been a long day for you, and this is material that I know reasonably well, so I can keep going and going. You guys are all pretty quiet. What happened? Did I lose you? Guys, your voice is breaking up. Someone is speaking, but I cannot hear clearly.
Yes, sir. You can continue, I guess, for a few more minutes. Okay.
So then let's do equation 3. Okay, I haven't talked about memory-based dependencies as yet, but let's do equation 3 before we take a break. Okay. On example 3, not equation 3, sorry. Can I change the sharing? Are you seeing my notes, my pad?
Yes, sir.
Yes, sir.
Yes.
So now in the third example, we are accessing the array C, and that function is C I minus 1 and Ci. Okay? So let me either change color or draw a different picture. Let me draw a different rectangle. And now my data space is like this, right? So I ask you the same question. When I'm executing iteration ij, which memory location am I reading in the first one? In the first reference, read reference on the right? it is I minus 1, right? So it is, this is I, it is this value that's being read. Okay? Which are the iterations that are writers into this? This whole row, right? Okay? Those are the iterations that write into the memory location being read. Out of those, which is the subset that is executed before the current iteration?
All of these.
All of them, right? And therefore, which of them is the most recent, the last one out of them? This one? You know, in the execution order, remember the execution order is row by row, left to right. So in the execution order, out of these iterations, this is the last one that was executed. So this iteration point depends on this iteration point. I'm getting rid of the memory. I'm not looking at it depends on or it reads which memory location. I'm going to get memory addresses completely out of the picture, and my dependencies are going to be functions or mappings from iteration points to iteration points. Okay? So any iteration point ij depends on the row I minus 1 m minus 1. Right? That is the mapping from iteration points to iteration points. This is the mapping from consumer to producer of values in the iteration space. And notice this is now not just a simple function like plus or minus 1 or a translation from the, from the point ij. It is now getting to be a somewhat complicated function. But it still happens to be a linear or affine function. It's a mapping from ij to I minus 1 n. And n is a parameter, and you think of parameters as additional indices, supplementary indices. Okay? I think it is time to take a break here. I will, let's take a break, and I will give you the precise mathematical formulation of this dependence analysis problem when we come back. Okay?